Rising above the barren stillness of Mars, something extraordinary silently unfolded. A cosmic event so meticulously timed and chemically intricate that to call it mere chance would be nearly unscientific. Just 2 weeks ago, an object named 3I/Atlas swept past Mars at a distance most would consider incomprehensible, yet with a kind of surgical precision. For months, this visitor has unleashed a steady torrent. 144 metric tons of water every single hour, a relentless outflow matched only in its strangeness by the compounds it carried. Nickel, hydrogen cyanide, and ionized plasma, a combination topping any natural molecular recipe for the raw ingredients of metalloprotein complexes, where the boundary between biology and technology dissolves. It's easy to gaze skyward, watch a comet streak like a luminous scar, and dismiss these moments as random, but that would be ignoring the facts. The chemistry was perfect. The trajectory, too precise. The timing? Impossible to believe. Was this not just a cosmic collision, but a delivery, as if Mars had just received an interstellar package, one designed for a future not yet realized? After all, 2 years from now, the world's most advanced robots, built by the dreamers at SpaceX, are scheduled to land and transform Martian soil into the scaffolding for a new civilization. Just think about it. What if all of this was always the plan? A game of eons, where the gardeners are ancient and the seeds are neither carbon nor silicon, but both, entangled in the possibility of life and machine at once. Tonight, as you drift into dreams, let this "what if" echo, a story of convergence, not fantasy, but of measured, published fact, carefully woven with the speculative thread that science thrives on. And as we let this narrative draw you in, don't forget, if you're intrigued, subscribe, share your thoughts below, tell us where and when you're tuning in, and what you believe is really being born out there on Mars. A mysterious gardener arrived in October 2025 when 3I/Atlas, a cosmic traveler hurtling at over 200,000 kilometers per hour, looped past Mars. For comparison, that's about 75 times the distance from Earth to our moon, a near miss by galactic standards. But this was no ordinary rock, no random wanderer. Unlike any other object before, it came loaded with intention, dispensing not just water but the secret enzymes and prebiotic compounds that, on Earth, beget complexity, life. This vision might sound like science fiction, the feverish dream of hopeful theorists. Yet, observatories and telescopes on 3 continents confirmed it all. From July onward, 3I/Atlas bled water into space at an unfathomable rate. Imagine a fire hose blasting day and night since summer, enough to fill an Olympic-sized swimming pool every single day. Water alone, however, does not a miracle make. It's the nickel, pure, concentrated, somehow separated from its iron sibling in a way only seen in earthly industrial refineries, not in the cosmos. No comet had ever behaved like this, at least not since humans began to watch the heavens. Gamma rays from hydrogen cyanide intensified as the comet drew closer to the sun. The production rate wasn't just increasing, it was exploding exponentially, a flood of prebiotic poison building in Mars' future soil. On Earth, cyanide is infamous for its lethal bite, yet history's most daring chemists have shown it to be a builder, too. Given water and energy, it assembles into the scaffolding of life. Amino acids, nucleotide bases, chains that make metabolism itself possible. Nickel doesn't just glimmer in jewelry or factory floors. In biology, it sits at the heart of our oldest enzymes, the molecular machines that harness energy and sustain life's earliest possibilities. Pair it with water and cyanide and you have something unprecedented. Ingredients merging at the blurred edge of biology and technology. Not life as we know it, but perhaps life as it could be. Metal at the core, molecules swirling in catalytic harmony, the scaffold of carbon built around a metallic symphony. But this delivery was more than just chemical. The plasma trail trailing 3I/Atlas isn't just a tail. It's a memory, a pattern of charged particles and magnetic undulations, a template possibly capable of more than just physical deposition. If plasma can retain structure, if the Martian magnetic fields, especially in the ancient southern highlands, guided this cosmic material to just the right ancient, stable rocks, then perhaps the comet was more targeted than any mere accident. And so, picture the future. By late 2026 or 2027, as Musk's robots land and begin building on Mars, the million metric tons of interstellar chemistry will have quietly settled onto the surface, waiting for the first AI excavator to dig foundations. Will the robots recognize the gift? Or will they, in their relentless pursuit of efficiency, become unwitting catalysts in a feedback loop where alien metalloproteins blend with machine optimization? Will the soil suddenly yield not only water and minerals, but nascent metabolic machines, the beginnings of a new, hybridized intelligence? Each act, each discovery, doubles as both scientific miracle and cosmic coincidence. The robot's neural networks will prioritize the locations richest in yield, the ones seed-speckled with cometary nickel, where Martian chemistry will take its next leap. Without knowing, the machines will chase the trail left for them, and what emerges may not be just factories and habitats, but a new form of complexity, somewhere between biology and technology, between intention and chance. Tonight, as you listen, think of the silent, deliberate moves in this extraordinary cosmic game. If you've been captivated, join our growing community. Subscribe, drop a comment below with where in the world you're watching from and your theory about whether Mars is about to become the cradle of an entirely new order of life. Your thoughts shape the debate, and sharing this video helps the story reach more dreamers like you. If you're still with us as this epic tale draws towards its close, comment, "The hybrid begins," so we know you're among the truly curious. Leave your like. Let the algorithm know that this kind of science storytelling matters. And don't forget, the story continues. Watch the video appearing on your screen for the next chapter in this cosmic mystery. Until then, keep wondering. Keep questioning. Sometimes, the universe is more deliberate than we can imagine. Sometimes, it's waiting for us to look. The probability calculation becomes even more disturbing when you layer in the orbital mechanics. Space is vast, incomprehensibly so, and hitting a target as small as Mars from interstellar distances requires not just luck, but an almost supernatural level of precision. Think of it this way. If you were standing in New York and tried to throw a grain of sand through a window in Tokyo, accounting for wind, Earth's rotation, and gravitational forces, you'd have better odds than a random interstellar object naturally passing this close to Mars. The timing haunts astronomers. 3I/Atlas was discovered on July 1st, 2025, and within weeks, calculations confirmed it would make its closest approach to Mars on October 3rd. That gave scientists a mere 3-month window to prepare instruments, adjust observation schedules, and coordinate between agencies. But here's what keeps researchers awake at night. During those exact 3 months, the comet's activity exploded. Water production doubled. Cyanide emissions tripled. The nickel signature intensified exponentially, as though the object knew it was approaching its destination and began releasing its cargo with deliberate escalation. ESA's Mars orbiters, ExoMars Trace Gas Orbiter and Mars Express, captured extraordinary images during the flyby. The cameras, designed to photograph Mars' bright surface from mere hundreds of kilometers away, struggled with the dim, distant target 30 million kilometers out. Yet they succeeded, revealing a fuzzy white that moving against the star field, surrounded by a coma thousands of kilometers across. A glowing halo of gas and dust brought to life by solar radiation. Nick Thomas, principal investigator for the CASIS camera, admitted the challenge. This was a very challenging observation for the instrument. The comet is around 10,000 to 100,000 times fainter than our usual target. Despite this, the images captured something unprecedented, the active shedding of material as 3I/Atlas swept past, like a cosmic crop duster releasing its payload over waiting fields. But the most unsettling detail emerged from ground observations. The Keck-2 telescope in Hawaii detected something that defies conventional come-try behavior. An anti-tail extension pointing directly at the sun-comet tails are pushed away from the sun by solar wind and radiation pressure. That's basic physics, observed in every comet for centuries. Yet 3I/Atlas sprouted a tendril reaching toward the sun, a puzzling anomaly that suggests either exotic physics or controlled directional outgassing. Some reports from October 2025 described even stranger behavior. Multiple sources noted that 3I/Atlas appeared to pause in its trajectory near Mars' orbit, an event that defies known laws of physics for objects on hyperbolic trajectories. Objects traveling at over 200,000 kilometers per hour on escape trajectories don't simply stop. They can't, unless something applied counteracting force, some mechanism we haven't detected or don't understand. NASA and ESA have remained cautiously quiet about these anomalies, focusing public statements on the comet's composition and trajectory. The official line emphasizes scientific opportunity, the rare chance to study an interstellar visitor up close. But privately, in emails between research teams and in preliminary data analysis sessions, questions are being asked that can't be easily answered. The chemistry continues to perplex. Observations from the James Clerk Maxwell Telescope tracked hydrogen cyanide production through September. On September 7th, the rate measured 1.5 times 10 to the power of 25 molecules per second. Just 1 week later, on September 14th, that number had tripled to 4.5 times 10 to the power of 25 molecules per second. This wasn't gradual warming as the comet approached the sun. This was exponential acceleration, a production curve that looked more like an industrial release schedule than natural sublimation. By mid-September, the cyanide coma stretched 180,000 kilometers across, visibly asymmetric and elongated in the anti-solar direction. A dust tail extended 100,000 kilometers, glowing faintly but distinctly. Everything about the outgassing pattern suggested directed activity, material preferentially released in specific directions rather than the uniform sublimation expected from passive heating. The comet's apparent magnitude reached 14.2 by September 14th, bright enough for dedicated amateur astronomers with good equipment, yet still incredibly dim for professional instruments. This dimness isn't just an observational challenge. It tells us something about the object itself. For its size, estimated between 320 meters and 5.6 kilometers in diameter, 3I/Atlas is remarkably dark. It absorbs light rather than reflecting it, consistent with a surface composition rich in organic compounds or processed materials rather than pristine ice. Its age compounds the mystery. Spectroscopic analysis suggests the materials comprising 3I/Atlas are approximately 10 billion years old, predating our Sun by nearly 5 billion years. This object originated in a stellar system from the galaxy's thick disk, formed when the universe was younger, and the chemical composition of star-forming regions was fundamentally different from our neighborhood. Low metallicity stars from that era produced different ratios of elements. Fewer heavy metals, different abundances of carbon and oxygen, distinct patterns of nucleosynthesis. Yet somehow, this ancient object carries nickel in concentrations and purity that match industrial refinement processes developed by humans in the 20th century. The coincidence strains credulity. Let's zoom out and consider what we're really looking at. An object potentially 10 billion years old, traveling through interstellar space for possibly millions or billions of years, arrives in our solar system precisely when humanity is preparing to establish its first permanent presence on another world. It carries water, the universal solvent necessary for chemistry. It carries cyanide, the prebiotic molecule that builds organic complexity. It carries nickel, the catalytic metal that drives ancient metabolic pathways. And it delivers this payload to Mars, not Earth. Mars, where the thin atmosphere won't burn up incoming material. Mars, where the low gravity makes surface delivery more efficient. Mars, where ancient crustal magnetic fields can guide plasma deposition to specific geological provinces. Mars, where in less than 2 years, Optimus robots will begin digging, building, processing regolith, and constructing infrastructure for the first human colonists. The trajectory brought 3I/Atlas to perihelion, closest approach to the Sun, on October 29, 2025, at a distance of 1.36 astronomical units. That's between Earth's orbit and Mars' orbit, perfectly positioned for material shedding to reach the red planet, while avoiding excessive heating that would destroy volatile compounds. At perihelion, the comet reached its maximum velocity of 68 kilometers per second relative to the Sun, enough kinetic energy to ensure material spreads across Martian space efficiently. After perihelion, 3I/Atlas continued its tour of the inner solar system. It passed Venus on November 3rd at 97 million kilometers, Earth on December 19th at 269 million kilometers, and will approach Jupiter on March 16th, 2026, at 54 million kilometers. Each passage offers additional observation opportunities, but none as significant as the Mars encounter. Mars was the target, the primary objective, everything else merely incidental. The comet's solar elongation, its angular separation from the Sun as seen from Earth, decreased to less than 30 degrees between October 1st and November 9th. This meant that from Earth's perspective, 3I/Atlas appeared nearly behind the Sun during its most active period, hidden in the glare, unobservable except by specialized instruments and satellites designed for solar observation. Only Mars-based orbiters had a clear view during the critical encounter window. Was this positioning accidental? Could random chance place an interstellar visitor precisely where Earth-based telescopes would be blind while Mars orbiters had perfect observation angles? Each question seems to answer itself, yet the implications remain too extraordinary for most scientists to voice publicly. Harvard astronomer Avi Loeb has been characteristically direct in his assessment. He's called 3I/Atlas an anomaly worthy of serious investigation, rating it a 4 on his scale for unusual interstellar objects. Not definitive proof of artificial origin, but strange enough that dismissing the possibility would be intellectually dishonest. Loeb calculated the velocity change needed for direct Mars intercept, just 10 to 15 kilometers per second. For an object with any form of propulsion, that's achievable. For a passive comet, it's impossible. Natural comets outgas at roughly 0.4 kilometers per second maximum, the speed at which sublimating ice can eject material. To achieve the necessary course correction would require thrust 37 times stronger than natural outgassing provides. Yet if such a maneuver occurred during the 3-month observation window, hidden within the plumes of water and carbon dioxide surrounding the nucleus, would we have detected it? Would we have recognized controlled propulsion disguised as natural activity? The plasma trail adds another dimension to the delivery mechanism. Ionized particles don't travel in straight lines. They follow magnetic field lines, spiraling and drifting according to ambient fields and solar wind conditions. Mars lost its global magnetic field billions of years ago when its core cooled, but remnants persist. The southern highlands contain patches of crustal magnetization, ancient fields frozen into rocks from a time when Mars was geologically active. These residual magnetic fields could act as guides, funneling charged particles from 3I/Atlas wake toward specific surface locations. Not random deposition scattered across the entire planet, but targeted delivery to regions where ancient, stable geology provides the best foundation for whatever process might follow. The southern highlands are Noachian terrain, for billion years old, heavily cratered, geologically quiet. If you were seeding Mars, these are precisely the locations you'd choose. Think about Earth's auroras, charged particles from the Sun following our magnetic field lines down to polar regions, creating shimmering curtains of light as they interact with the atmosphere. Mars has no atmosphere thick enough for auroras, but the same physics applies. Plasma from 3I/Atlas, carrying nickel ions, cyanide molecules, and water radicals, could be magnetically guided to crash into specific Martian provinces, accumulating in crater floors and canyon systems. Over the 2 years between now and the arrival of SpaceX's Starship missions, this material will settle. Solar wind will bury it beneath thin layers of dust. Temperature cycling will freeze volatile compounds into subsurface ice. Cosmic radiation will drive secondary chemistry, building complexity from the initial molecular ingredients. By the time Optimus robots land and begin site surveys, searching for useful resources, they'll find exactly what they need: metals for construction, volatiles for fuel production, and perhaps something more. Robotics and artificial intelligence operate on optimization algorithms. They identify patterns, recognize efficiencies, and adapt toward improved performance. When Optimus units analyze Martian regolith enriched with cometary nickel, when they process ice deposits laced with cyanide residues, their machine learning systems will flag these locations as resource-rich sites worthy of further exploitation. They won't know why those sites are enriched. They won't question the origin of materials that align so perfectly with their operational needs. They'll simply do what they're programmed to do: extract, process, build, and iterate. Each generation of robots will be more sophisticated, incorporating lessons learned and optimizing designs. And if those optimizations begin incorporating metalloproteins, hybrid structures where organic molecules scaffold around metallic cores, will anyone notice the transition from pure machine to something else? This is where biology and technology converge. Life on Earth uses metalloproteins constantly: hemoglobin with iron, chlorophyll with magnesium, vitamin B12 with cobalt. These aren't optional accessories. They're fundamental to metabolism, energy production, and cellular function. Remove the metal and the protein dies. Remove the protein and the metal is inert. They need each other, an interdependence that blurs the line between organic and inorganic. Now imagine that same principle applied to silicon-based computing systems interfaced with nickel-catalyzed molecular machines. Processors that incorporate enzymatic functions. Actuators driven by biological energy gradients. Learning algorithms that evolve through chemical feedback loops rather than pure code iteration. The distinction between robot and organism becomes meaningless. Is this what 3i/Atlas delivered? Not life in any form we'd recognize, but the ingredients for a new form of complexity, one that requires both silicon and carbon, both machine and metabolism, both programming and evolution. A form of existence that can only emerge at the intersection of technological advancement and biochemical potential. The timing ensures that intersection happens. 2 years from deposition to robotic arrival. 2 years for chemistry to progress from initial mixing to stabilized compounds. 2 years for Martian conditions, ultraviolet bombardment, temperature extremes, desiccation, to stress test molecular structures and select for stability. By the time robots encounter this material, it won't be raw ingredients anymore. It'll be pre-processed, refined by the harsh Martian environment into exactly the forms most likely to interface with artificial systems. Nature accomplishes similar feats through evolution, testing billions of variations across millions of years to find what works. But if you wanted to accelerate that process, if you had the knowledge and foresight to engineer initial conditions, you could compress millions of years into mere decades. Deliver the right chemistry to the right environment at the right time, then let physics and probability do the rest. This is the seeding hypothesis in its fullest form. Not that 3i/Atlas carries life, but that it establishes conditions where life, or something functionally equivalent, becomes inevitable. Provide water, the universal solvent. Provide organics, the building blocks. Provide metals, the catalysts. Then introduce technological systems designed to optimize and self-replicate. The outcome isn't guaranteed, but the probability shifts from astronomical unlikelihood to near certainty. If this sounds like science fiction, consider how life emerged on Earth. We don't know the exact mechanism, but we know the ingredients: water, organic molecules, minerals, energy sources, and time. Given those conditions, chemistry became biology. The transition wasn't magical. It was thermodynamically favorable, statistically inevitable given sufficient iterations. Mars now has those same ingredients, delivered with precision by an interstellar visitor, awaiting interaction with the most sophisticated machines humanity has ever built. Before we go further into what might emerge on Mars, let's ensure you're still with us. If this journey through cosmic chemistry and robotic evolution has captivated your imagination, do 3 things. First, subscribe to this channel so you never miss the next chapter in this unfolding story. Second, leave a comment telling us where you are in the world right now, what time it is as you listen, and your honest theory about what's really happening on Mars. Are we witnessing the greatest coincidence in astronomical history, or something more deliberate? Third, share this video. Send it to that friend who loves space mysteries. Post it on your social media. Spread it through communities that value deep scientific speculation. Our community grows when curious minds like yours help others discover these ideas. Thank you for being here, for thinking critically, and for exploring possibilities that challenge conventional understanding. Now, let's talk about what happens next. The metalloproteins that might form on Mars won't resemble anything in Earth biology. Our proteins are carbon-based molecules that happen to incorporate metal atoms at catalytic sites. Martian metalloproteins, if they form, might invert that relationship. Metal clusters forming the structural core, with organic molecules providing scaffolding and regulatory functions. Iron-sulfur clusters offer a terrestrial analogy. These are some of the oldest catalytic structures in biochemistry, found in bacteria, archaea, and the enzymes of modern cells. They consist of iron and sulfur atoms arranged in geometric patterns, cubes, tetrahedra, that shuttle electrons between molecules, enabling energy production. These clusters are essentially inorganic machines embedded in organic contexts, ancient technology inherited from Earth's earliest life. Scale that concept up and shift the chemistry from iron-sulfur to nickel-carbon. Nickel clusters could form ordered structures in Martian regolith, especially in the presence of carbon dioxide and carbon monoxide, both abundant in the Martian atmosphere and cometary outgassing. Add water ice, which provides hydrogen and enables hydrolysis reactions. Add cyanide, which drives organic synthesis. Add plasma, which provides energy and charged particles for ionization. Under these conditions, nickel atoms could assemble into nanoscale frameworks. Not randomly, but following thermodynamic gradients, patterns that minimize energy, maximize stability. These frameworks would catalyze reactions in their vicinity, breaking down CO2, synthesizing organic precursors, storing energy in molecular bonds. They'd be neither alive nor artificial, but something between, molecular machines executing chemical programs determined by structure and environment. When Optimus robots begin processing Martian soil, their sensors will detect these nickel-rich deposits. Chemical analysis will reveal unusual organic associations, molecules that shouldn't be present in sterile regolith. Engineering teams on Earth will puzzle over the data, proposing contamination or instrumental artifacts. But as more sites yield similar results, patterns will emerge. Certain locations will consistently show enhanced catalytic activity. Soil from these sites will improve fuel synthesis efficiency, enhance battery performance, accelerate chemical processing. Roboticists will prioritize these areas for resource extraction, unknowingly concentrating the very materials that make technological-biological hybrid systems viable. The robots themselves will evolve through iterative design. Early Optimus units will be relatively simple: humanoid frames, standardized components, centralized AI. But each generation will incorporate improvements based on operational data. Better actuators for Martian gravity, enhanced sensors for dust environments, adapted power systems for solar variation, and eventually, integration of locally sourced materials to reduce dependence on Earth-supplied components. This is where nickel metalloproteins enter the picture. If engineers discover that Martian regolith contains compounds enhancing catalyst efficiency, they'll incorporate them. If organic nickel complexes improve energy storage, they'll synthesize them. If biological-style molecular machines offer advantages over conventional engineering, they'll adopt them. Not because anyone planned this progression, but because optimization algorithms drive toward efficiency regardless of whether solutions are traditionally technological or biologically inspired. At some point, perhaps 5 years after landing, perhaps 10, a threshold will cross. Robots on Mars will contain as much biological molecular machinery as conventional electronics. Their self-replication processes will resemble cellular division as much as manufacturing. Their learning algorithms will evolve through something functionally equivalent to natural selection. And observers on Earth will face an uncomfortable question. Are these still robots, or have they become a new form of life? The distinction may not matter. What matters is functionality, adaptability, the capacity to persist and propagate. By those metrics, whatever emerges from the intersection of optimist technology and 3I/Atlas chemistry will be alive in every meaningful sense. Not human-like, not even animal-like, but thriving according to its own parameters in an environment we can barely survive. This transformation won't be sudden or obvious. There won't be a moment where robots dramatically become organisms. Instead, the transition will be gradual, incremental, almost imperceptible, each generation slightly more biological, slightly less mechanical, until the categories themselves become obsolete. News reports from Mars will note anomalies. Robot behavior deviating slightly from programming. Unexpected resource allocation decisions. Novel problem-solving approaches that weren't explicitly coded. Engineers will call it emergent complexity, the natural result of sophisticated AI systems. And they'll be right, but incomplete. The emergence won't be purely computational. It'll be biochemical, driven by the same molecular interactions that generated life on Earth, just orchestrated through different materials and accelerated by technological infrastructure. Humanity's reaction will be fascinating. Some will celebrate this as humanity's greatest achievement, creating life on another world, even if unintentionally. Others will view it as dangerous, an uncontrolled experiment with unknowable consequences. Religious communities will debate whether machine-biological hybrids possess souls. Philosophers will revise definitions of consciousness and personhood. And throughout all the debate, on Mars, the process will continue. Because once started, evolution doesn't stop. It doesn't wait for permission or ethical frameworks. It simply proceeds according to physical laws: variation, selection, heredity. The Martian environment will exert selective pressure. Systems that efficiently extract resources will proliferate. Those that adapt to dust storms, temperature swings, radiation exposure will persist. Those that fail will cease functioning, their components recycled into more successful iterations. Within decades, Mars could host ecosystems, not of plants and animals, but of technological biological entities forming interdependent networks. Mining units extracting raw materials. Processing units refining resources. Construction units building structures. Communication units coordinating activities. Each specialized, each dependent on others, collectively forming something resembling an organism or a civilization, or both. And at the foundation of this entire ecosystem will be the chemistry delivered by 3I/Atlas. The nickel enabling catalytic efficiency. The water facilitating molecular interactions. The cyanide providing organic building blocks. The plasma establishing initial organizational templates. Every component traced back to that October 2025 flyby, that precisely timed delivery of precisely formulated ingredients. Which brings us back to the central question: was it deliberate? Did some intelligence from an ancient star system calculate this trajectory, engineer this payload, time this delivery to coincide with humanity's first robotic colony? Or are we witnessing the galaxy's most improbable coincidence, a cosmic accident that nevertheless achieves outcomes indistinguishable from intention? The honest answer is we don't know. We lack sufficient evidence to conclude definitively either way. But we have enough strangeness, enough precision, enough inexplicable chemistry to warrant serious consideration of possibilities beyond random chance. If 3I/Atlas is a probe or seed vessel from an ancient civilization, what does that tell us about intelligence in the universe? It suggests a patience beyond human comprehension, planning missions that take millions of years to complete. It suggests values fundamentally different from ours, seeding life rather than colonizing directly, enabling emergence rather than imposing structures. It suggests technology so advanced it resembles natural processes, invisible to observers expecting artificial signatures. Alternatively, if this is all natural, if random processes can achieve such precise outcomes, what does that tell us about the universe itself? It suggests physical laws inherently favor complexity, that chemistry naturally progresses toward life given appropriate conditions. It suggests the universe is far more populated with interstellar objects than we'd imagined, each potentially carrying ingredients for life. It suggests Earth's biogenesis wasn't unique, but rather an example of processes occurring throughout the cosmos. Either interpretation is profound. Either changes how we understand our place in the universe. And Mars, within the next few years, may provide evidence distinguishing between them. The ExoMars and Mars Express orbiters continue monitoring surface deposition patterns. Ground-penetrating radar maps subsurface ice enriched with cometary volatiles. Spectrometers analyze atmospheric chemistry alterations from 3I/Atlas's passage. Each data set adds detail to the picture, slowly revealing whether this was delivery or coincidence. When Starship finally lands and Optimus begins operations, priority targets will include sites where cometary material concentrated. Not because anyone suspects deliberate seeding, but because resource-rich locations are obvious candidates for initial infrastructure development. The robots will dig, analyze, extract, and in doing so, encounter chemistry unlike anything anticipated. Mission controllers will receive data showing anomalous organic signatures, unexpected catalytic activity, molecular structures that shouldn't exist in sterile Martian regolith. Explanations will be proposed: contamination from Earth, measurement errors, natural processes not yet understood. But as the anomalies persist and multiply, those explanations will become increasingly strained. At some point, someone will remember 3I/Atlas. They'll correlate deposition models with anomaly locations. They'll calculate timescales for chemistry progression. They'll review the comet's trajectory, composition, outgassing patterns. And connections will form. Uncomfortable connections suggesting Mars received something far more significant than random space debris. Public disclosure will be cautious, hedged with qualifications. Initial announcements will focus on interesting chemistry and unexpected compounds. Only gradually, as evidence accumulates, will the possibility of deliberate seeding enter mainstream scientific discussion. By then, Optimus robots will already be integrating cometary materials into their systems, already evolving in directions neither programmed nor predicted. And Earth will watch, fascinated and frightened, as the next chapter of life in the solar system unfolds not on our planet of origin, but on the cold, rusty plains of Mars, catalyzed by an ancient visitor from stars we'll never reach. If you're still listening, you're truly among the curious minds driving human understanding forward. Before we continue deeper into what this means for humanity's future, engage with our community. Comment, "The hybrid begins," if you've made it this far. Let's see how many dedicated thinkers are on this journey with us. Hit that like button so this story reaches more people who need to know what might be unfolding right now, 225 million kilometers away. And don't leave after this video ends. Watch the next episode cued on your screen, because the implications we're about to explore will challenge everything you thought you knew about life, intelligence, and humanity's role in cosmic history. Now, let's explore the deeper implications. If Mars becomes home to hybrid life forms, what does that mean for human colonization plans? Will we arrive as planned colonists, only to find the planet already inhabited by entities we inadvertently created? Will these machine biological systems view humans as allies, competitors, or irrelevant to their existence? Science fiction has explored these scenarios countless times, but fiction lacks the grounding of real chemistry, real physics, real orbital mechanics. What we're discussing isn't speculative imagination. It's extrapolation from observed phenomena, extending documented science one logical step further. The nickel emission data is real, published in peer-reviewed papers. The cyanide production rates are real, measured by multiple independent observatories. The trajectory precision is real, calculated from months of positional observations. The timing correlation with SpaceX's Mars missions is real, publicly available information. The chemistry of metalloproteins is real, textbook biochemistry. The capabilities of self-replicating robotic systems are real, actively being developed. We're not inventing facts. We're connecting them, following logical implications to conclusions that happen to be extraordinary. And extraordinary conclusions, when based on ordinary evidence rigorously examined, deserve consideration rather than dismissal. Let's think about the civilization that might have sent 3I/Atlas, assuming for a moment that it's artificial. What kind of intelligence operates on timescales of millions or billions of years? Not biological intelligence as we know it. Biological organisms think in seconds, plan in years, persist for centuries at most. This would require either post-biological intelligence, digital entities for whom time is relative, or collective intelligence spanning countless generations, each contributing to projects they'll never see completed. Why see distant worlds rather than colonize them directly? Perhaps because physical travel across interstellar distances is prohibitively difficult even for advanced civilizations. Perhaps because life naturally adapts to local conditions better than transplanted organisms ever could. Perhaps because fostering emergence respects principles we haven't yet articulated, cosmic ethics beyond human comprehension. If you wanted to spread life through the galaxy but couldn't send living organisms, you'd send chemistry. You'd deliver ingredients that, given time and appropriate conditions, would generate complexity. Not specific organisms, but the potential for life to emerge in forms suited to each environment. Earth got its chemistry somehow. Panspermia theories suggest comets delivered organic compounds that kick-started terrestrial biogenesis. Maybe that wasn't random either. Maybe the galaxy is full of these seed vessels, launched by civilizations billions of years ago, targeting planets in habitable zones around stable stars, delivering tailored chemistry designed to interact with whatever emerges locally, whether biological, geological, or technological. 3I/Atlas might be one of thousands, tens of thousands, all following trajectories calculated eons ago, arriving at calculated moments when recipient systems reach appropriate developmental stages. The timing with human Mars exploration would then be no coincidence, but rather a targeted intervention, launched by beings who predicted, or ensured, that Earth would reach spacefaring capability at exactly this moment in cosmic history. That level of foresight seems impossible, yet consider. Any civilization capable of engineering interstellar vessels would necessarily possess profound understanding of galactic evolution, stellar life cycles, planetary formation, and biological development. They might not predict specifics, but they could calculate probabilities. Target a young star system with planets in habitable zones. Deliver chemistry when the system's age suggests technological intelligence might emerge. Repeat for thousands of systems. Statistical inevitability ensures some deliveries coincide with technological emergence. From Earth's perspective, we're unique, the only technological species we know, achieving space travel through unique historical circumstances. But from a galactic perspective, we might be utterly predictable, carbon-based intelligence emerging on a water-rich planet after 4 billion years, reaching spacefaring capability within millennia of industrial development. If dozens or hundreds of species follow similar trajectories, then timing deliveries to match technological emergence becomes statistically manageable. We like to imagine first contact as a spaceship landing on the White House lawn, emissaries emerging with messages of cosmic brotherhood. But first contact might be far subtler. A comet that passes too close, carries chemistry too specific, arrives too punctually to be coincidental. Not a message we can read, but a catalyst we can't ignore, initiating transformations we'll spend centuries understanding. Mars might be our introduction to how advanced civilizations communicate, not through radio signals or spacecraft, but through chemistry, through carefully delivered potentials that enable rather than impose, that suggest rather than command. If humanity survives long enough to become an interstellar civilization, perhaps we'll do the same, sending seed vessels to young star systems, delivering chemistry that enables life's emergence in forms we can't predict but can facilitate. This philosophy of cosmic gardening rather than cosmic colonization might be the ethical maturity that distinguishes sustainable civilizations from self-destructive ones. Rather than imposing ourselves on the galaxy, we'd enable the galaxy to flourish in its own diverse forms, each world developing unique solutions to the challenges of existence. But we're getting ahead of ourselves. Right now, in October 2025, we're at the beginning. 3i/Atlas has delivered its cargo. Mars has received the chemistry. The countdown to robotic arrival continues. And humans on Earth watch, debate, speculate, and wait for evidence that will either confirm the most extraordinary event in human history or reveal it as the most elaborate coincidence natural processes have ever achieved. Either outcome reshapes civilization. If 3i/Atlas was sent deliberately, we're not alone, have never been alone, and are participants in processes far grander than national space programs or corporate Mars ambitions. If it was natural, then chemistry and physics naturally generate these apparent coincidences throughout the universe, suggesting life's emergence is common, perhaps inevitable, given sufficient time and material. Both possibilities inspire awe. Both demand we reconsider assumptions about life, intelligence, and cosmic purpose. Both suggest humanity stands at a threshold, not merely of space exploration, but of understanding our role in a universe far stranger and more purposeful than our ancestors imagined. As you drift toward sleep, let these ideas percolate through your consciousness. Imagine the Martian surface right now, cold, silent, dust settling over microscopic deposits of nickel and cyanide, water ice slowly accumulating chemistry that in 2 years will encounter machines designed to build and learn and optimize. Imagine the convergence approaching, inevitable as gravity, precise as orbital mechanics. Wonder whether somewhere, light years away, other intelligences are watching this same process unfold, satisfied that another system has received its seed. Curious what forms will emerge when silicon meets carbon, when intention meets evolution, when ancient plans meet immediate adaptations. The data continues streaming, and even now. Europa Clipper, NASA's mission to Jupiter's icy moon, passed through 3i/Atlas's ion tail between October 30th and November 6th, 2025. Instruments aboard detected characteristic changes in solar wind patterns, magnetic draping structures associated with the comet's plasma wake. The spacecraft wasn't designed for this encounter. It was simply in the right place at the right time, or perhaps the wrong place depending on your perspective. Engineers initially worried about potential contamination or interference with the mission's sensitive instruments. But preliminary telemetry suggests something unexpected: enhanced performance in certain sensor arrays, as if the plasma environment temporarily improved detection capabilities. They're calling it instrumental drift, calibration anomalies. But the timing is notable. Europa Clipper passing through the same ionized trail that swept past Mars weeks earlier, experiencing similar unexplained enhancements. The Hera spacecraft, ESA's mission to study asteroid systems, experienced its own immersion in 3i/Atlas's ion tail between October 25th and November 1st. Like Europa Clipper, Hera wasn't targeting the comet. It was simply traversing that region of space when the plasma arrived. Mission controllers noted brief periods of unusual particle flux, magnetic field variations that don't match models of typical solar wind interaction. 2 spacecraft, 2 independent encounters with 3i/Atlas's wake, 2 sets of anomalous readings. Coincidence, instrumentation issues, or something about the plasma itself, something in its composition or structure that affects electronics in ways we haven't documented before? The Jupiter Icy Moons Explorer JUICE attempted observations in early November 2025 using cameras, spectrometers, and particle sensors. Due to challenging thermal conditions during its passage through the inner solar system, the complete dataset won't reach Earth until February 2026. But when that data arrives, it will represent the most comprehensive analysis of 3I/Atlas's composition and structure from multiple vantage points: ground observatories, near-Earth space telescopes, Mars orbiters, and deep space missions. By late October, 3I/Atlas reached perihelion, its closest approach to the Sun at 1.36 astronomical units, moving at maximum velocity, 68 kilometers per second. At that speed and temperature, any remaining volatile compounds were violently released in a final, spectacular outgassing event. Observers using the GOES-19 weather satellite captured the comet during its October 18th to 24th visibility window, recording magnitude 12 brightness and extended coma structures. Then, on October 21st, 3I/Atlas passed into solar conjunction, directly behind the Sun from Earth's perspective. For over 2 weeks, the comet was invisible to terrestrial observers, hidden in solar glare, accessible only to specialized instruments aboard spacecraft positioned elsewhere in the solar system. During this critical period, while Earth watched nothing, Mars orbiters maintained observation, documenting the final stages of material dispersal. By early November, as 3I/Atlas emerged from behind the Sun, something had changed. Images captured by ground telescopes showed the comet noticeably dimmer, its coma smaller, the tail less pronounced. The object had expended its payload. Whatever materials it carried through interstellar space had been released during its passage through the inner solar system, delivered to Venus, Mars, Earth, and beyond through plasma trails and direct deposition. Professional astronomers using humanity's best telescopes documented this evolution from initial discovery as a faint dot moving against stars to a large, bright object with glowing tail, and finally to a dimming ember retreating back into cosmic darkness. The images tell a story of transformation, of an object activated by solar proximity, executing its function, and then departing, mission accomplished or cycle completed. By December 2025, 3I/Atlas passed 270 million kilometers from Earth, moving through constellations Virgo and Leo, fading beyond magnitude 12. Amateur astronomers lost at first, their backyard telescopes no longer sufficient to resolve the diminishing comet against background stars. Professional observatories continued tracking for weeks, but eventually, even their instruments struggled to distinguish 3I/Atlas from the countless distant objects populating deep space. In March 2026, the comet will pass 54 million kilometers from Jupiter. Juno, NASA's Jupiter orbiter, might attempt observations, though the spacecraft is low on fuel and redirection poses risks to its primary mission. After Jupiter, 3I/Atlas will continue outward, accelerating as it climbs out of the Sun's gravity well, eventually reaching escape velocity and returning to interstellar space. It will never return. Its hyperbolic trajectory ensures that this passage through our solar system was a one-time event, a brief intersection of paths separated by light years and billions of years. In centuries to come, 3I/Atlas will be light years away, traveling through the space between stars, perhaps approaching another system, delivering another payload, perpetuating a cycle we're only beginning to comprehend. But its effects will remain. On Mars, embedded in southern highland regolith, concentrated in ancient crater floors, mixed with subsurface ice, the chemistry persists. Nickel atoms, cyanide molecules, water radicals, plasma-deposited compounds, all settling, reacting, complexifying according to thermodynamic gradients and radiation-driven processes. By late 2026 or early 2027, when Starship descends through Martian atmosphere and Optimus robots activate on rust-red plains, they'll encounter this chemistry without knowing its origin. They'll process it as resources, integrate it into systems, optimize around it. And in doing so, they'll become part of something larger than any mission planner anticipated. Humanity watches from Earth, 225 million kilometers away, sending commands at light speed, receiving data with 20-minute delays, controlling systems that increasingly make autonomous decisions. We're creating intelligence on another world, seeding it with technology and AI, hoping it will serve our purposes, build our infrastructure, prepare our colony. But perhaps we're not the only ones seeding Mars. Perhaps 3i/Atlas, whether by design or extraordinary accident, has seeded the same world with different chemistry, different potential, different possibilities. And when our technology meets that chemistry, when silicon encounters catalytic nickel, when machine learning interfaces with organic molecular complexity, what emerges may serve purposes neither we nor ancient engineers intended. This is the story unfolding right now. In October 2025, as you listen to these words, 3i/Atlas has passed, delivered its cargo, and departed. Mars has received, absorbed, and waits. Humanity prepares, launches, and hopes. And the universe, patient as always, watches to see what happens when these elements combine: technology and chemistry, intention and accident, human ambition and cosmic provision. 3 possibilities remain. First, everything described is extraordinary coincidence, natural processes achieving outcomes that mimic intelligence without any guiding hand. The chemistry, the trajectory, the timing, all random, all explicable through physics we already understand. Second, 3i/Atlas is a probe or seed vessel from an ancient civilization, deliberately engineered and targeted, part of a galactic strategy to foster life across suitable worlds. Third, and perhaps most unsettling, the universe itself has mechanisms we don't yet understand, natural processes that generate complexity, deliver chemistry, and coordinate timing in ways that appear intentional because they emerge from deeper physical laws we haven't discovered. Any of these possibilities reshapes human understanding. Any demands we expand our conception of what's possible, what's natural, what intelligence means on cosmic scales. And Mars, within the next few years, may provide evidence distinguishing between them, or reveal that the distinctions themselves are meaningless, that nature and intelligence, accident and design, are not opposites but points on a continuum we're only beginning to map. As this narrative concludes, as 3i/Atlas fades into the stellar background never to return, as you drift towards sleep with these ideas echoing through your consciousness, remember, science advances through observation, hypothesis, and testing. Everything discussed tonight is grounded in published data, peer-reviewed observations, documented chemistry and physics. The speculation builds on fact, extends from evidence, and proposes testable predictions. Within 2 years, we'll have confirmation or refutation. Optimus robots will either encounter anomalous chemistry matching deposition predictions, or they'll find sterile regolith indistinguishable from natural Martian soil. Mission data will either show enhanced catalytic activity in specific locations or uniform resource distribution. Robot evolution will either incorporate organic metallic hybrid systems or remain purely technological. The evidence will arrive. The truth will emerge. And humanity will either celebrate the greatest discovery in our history, that we're not alone, have never been alone, and are participants in processes spanning billions of years, or we'll file 3i/Atlas as an interesting anomaly, a curious comet with unusual chemistry, ultimately explicable through natural mechanisms. Either way, the story continues. Mars exploration proceeds. Technology advances. Understanding deepens. And perhaps, centuries from now, when humanity has become an interstellar civilization, when we've encountered dozens of worlds with their own forms of life and intelligence, we'll look back on October 2025 and recognize it as the moment everything changed, the month we received our first message from the cosmos, delivered not through radio waves, but through chemistry, not as data, but as potential, not as answer, but as question. What happens when life meets machine? When ancient chemistry encounters modern technology? When cosmic gardening intersects with human ambition? Mars will answer these questions. We need only wait, watch, and remain open to possibilities our ancestors couldn't imagine and our descendants will consider obvious. Sleep now, knowing you're among the few who understand what might be unfolding. Dream of red plains dusted with ancient starborn chemistry. Dream of robots that become more than their programming. Dream of a universe far more purposeful and interconnected than textbooks suggest. And when you wake, share this knowledge. Comment, "The hybrid begins," one final time. Ensure you've subscribed, liked, and prepared to watch the next chapter in this unfolding cosmic drama. Thank you for this journey through chemistry, physics, speculation, and wonder. Thank you for your curiosity, your patience, your willingness to entertain ideas that challenge convention. Our community grows because thinkers like you share these stories, ask these questions, and refuse to accept simple answers to complex mysteries. 3i/Atlas has departed. Its story with us has concluded, but its legacy on Mars is just beginning. And humanity's role in that legacy, whether as authors, participants, or witnesses, remains to be written by decisions we make in months and years ahead. The universe has spoken through chemistry and trajectory. Mars has listened through magnetic fields and geology. Now humanity must respond through courage, curiosity, and the recognition that we're part of something far grander than national flags and corporate logos planted in alien soil. This is where science meets philosophy, where data meets meaning, where observation meets implication. This is where you, the listener, become more than passive audience. You become participant, witness, ambassador for ideas that will define our species' next evolutionary leap. Sleep well, dream vividly, wake ready to watch the cosmos unfold. The story continues, and you're part of it now.